Closed. Our first speaker in this session is Justin Hiemstra from the Pelican Project at Path and Morgridge. Again, I'm not going to try and pronounce his talk title because I think he's going out of his way to give me a tongue twister. But Justin is at the intersection of the bird and the snake here, and so we will leave you to whatever terrifying Gen AI pictures you can create in your own mind for that. So thank you, Justin.
Thanks, Greg. All right, so one thing to know about me, I work at CHTC, but I also work at the Morgridge Institute for Research. And occasionally that means I get loaned out to help researchers that aren't a part of our usual community. They're the biologists that may use CHTC resources, but aren't as into the computing stuff. And so I'm not wearing my Pelican hat right now. I'm wearing my software engineer to help other biologists hat. So before I get started, this is something we talked a little bit about yesterday in our panel. I think broadly there are kind of two types of research software. The first type is generally the type that I work on. These are kind of long-term projects. They have long-lived funding streams. They don't live by the usual publish or die life cycle. The second type are those publish or die life cycle type projects. So PhD grad students, people working really hard to meet paper deadlines. And you often end up with the kind of software that generates commit messages like this. So today, I have a story of running other people's type 2 research software at scale. This project starts with Tony Gitter, who you should all recognize. He was our keynote speaker last year, and one of his colleagues, Anna Ritz from Reed College. Now, they're biologists. Marone would say they like to deal with the stinky stuff. And they start off here with an observation that there's a lot of experimental data that does work to connect different types of proteins. So protein A, in some way, is connected to protein B. For us, this looks like a DAG of, or not a DAG, but a graph of different nodes with connected edges. And one of the key questions that biologists like to ask about these different protein-protein interaction networks is, if I start at point A and I want to get to point B, maybe I'm trying to create some kind of therapeutic where I can target one protein and that in fact regulates another protein, what path do I traverse through this graph? Now, in this field of research, there are lots of different algorithms that try to come up with some clever way to generate one of these subpaths. But the problem is that a lot of these different algorithms are this type 2 research. So they're not necessarily meant to be picked up and used by people who actually want to do real science. So Tony and Anna, they get together and they ask the question, what if we created a tool that was able to piece together all of these different types of type 2 research so that a researcher who does have real data and wants to apply these algorithms to it is able to run this in a streamlined format? And this is where SPRAS comes in, the Signaling Pathway Reconstruction Streamliner. In computer science, we're fond of this quote. We say that all problems can be solved with another level of indirection, except for the problem of too many levels of indirection. I actually think Shakespeare beat David Wheeler to it. So he writes in Hamlet that by indirections, find directions out. Okay, so how do we go about doing this in SPRAS? The first thing to note is that we present the researcher with a universal input and output data format. So if you're going to use SPRAS, you only need to know what your data looks like in one case. So universal input, universal output. The next level of this is that inside of SPRAS, there's this conversion framework. So we take this universal input and we convert it into some kind of data that is understood by the particular algorithm, the particular pathway reconstruction method that we're interested in running. As Marone said earlier, it's really nice to have containers. And so the approach that Tony and Anna take in this is that each of these different type 2 algorithms that we want to bundle is given its own containerized environment. We see in some of these that there may be some dependency on a particular file path being accessible, or something needs to be bound to a specific port, or something needs to be run by a specific user. So sticking these inside of containers is a great way to get around the portability aspect of running these. The next piece of this is, how do we actually how do we actually combine all of these into a workflow that we can reproduce and that doesn't require manual steps and control? So Tony and Anna decided that they were going to use Snakemake. I think it's important to note that Snakemake is a workflow management tool. It's a lot like DAGman for those of you who are Condor folks, and it's widely used in the bioinformatics community. So these are a few of the niceties that you get with Snakemake. It's rule-based and declarative. So rather than saying do X, we say produce X. So we take an input file, we apply some kind of function to that input file, and we produce an output file. It has a few other nice things that come with workflow management, the ability to determine which sections of the workflow need to run, maybe which need to be rerun, those kinds of things. And really nicely for us, it's Pythonic. So this snake file over here is kind of a hello world example of how you might stitch together these workflow steps. And one thing I'll note is that you can actually write plain Python in the snake file, which is really nice. So one of the key things that we get out of this is that Snakemake has this concept of wildcards. We can say that this general workflow can be applied to different types of data, and doing this lets us kind of build this type of structure here where data 1 turns into derived 1, data 2 turns into derived 2, etc. So we don't need to design specific workflows for specific datas. So why not just use DAGman, right? We already have a tool that does this. Why go through all the effort of building this into Snakemake? I think the key here is that Sprass existed before any attempt to try to run this at scale. And what that meant was that in order to keep this workflow something that can be passed off to other biologists who aren't tied into these Condor pools, we needed to keep it generic enough that it could be run by people who don't have access to CHTC or the OS pool. So that was an early design constraint. We needed to get this to work with Snakemake. We couldn't just redesign the whole thing and make it DAGman specific. All right, so at this point, we've been talking the last couple days about all hearing that little Marone voice in our heads. I think my Marone voice kicked in, and I started by asking, what would it take to run one algorithm with Sprass on one data set as only one job on one EP, kind of the simplest thing we could get running. Using this, what can we learn from the process? So this is a pretty familiar story for a lot of us who run workflows. First step is containerize the software, find some way to create a portable environment. Next, create a submit file that we can use to pass this work onto HTCondor, submit the job, find the bugs, solve the bugs, and iterate. Now, the first real hurdle that I encountered in this process was that containerizing Sprass introduced a dependency on nested containers. So remember, Sprass itself wants to run each of these different pathway reconstruction methods in its own container. So if I containerize Sprass, now I have to do nested containers in something like the OS pool. So I am not an expert in this kind of container stuff. I'd love for you experts, and I know there are a few of you in the audience, to come talk to me about some of this. But this is one of those things that was kind of difficult for me to figure out, and it took me a little bit to get right. My observations are that in our unprivileged computing environments, Docker is generally not your friend. So thank you, Aptainer, for being there to save the day. Another observation is that in order to keep Sprass generic and not redesign it to fit the OS pool, these jobs need to be able to pull Docker images from Docker Hub inside the job and convert those to a CIF that can then be launched as a part of the job. So this isn't some pre-declared CIF that Condor is transferring. It's something that has to happen dynamically in the job. So in developing this, kind of my go-to was, all right, let's see if I can Condor SSH to job. Let's see if I can play around with some different Aptainer commands, see if I can get things running. Okay, that doesn't work. What if I try a different combination of flags? Okay, that doesn't work. And eventually what I found out, the secret for me, was starting these inner Aptainer containers as unpacked CIF images. So this is passing the -- sandbox flag. This was pretty simple once I knew how to do it. Of course, figuring out how to do it was the hard part. Okay, so at this point, I'm able to take Sprass and as one big monolithic workflow, send it to one EP and run the job. The next step is asking what would it take for Snakemake to manage each of its different rules or jobs as individual Condor jobs so that we can actually do this in a distributed and kind of parallelized way. So luckily for me, Snakemake was thinking about this at the same time, the folks who maintain that. And they actually, as I was going through and developing the code to do this, they completely shook things up. They redesigned the whole Snakemake backend to introduce this ability to write plugins for executors. So for people like Condor, we can now write an executor that teaches Snakemake how to run Condor jobs. So I started working on one of these, and then after a month or two, I found out that Janis Speer here from the University of Dortmund, he beat me to it, and he did a really good job. So I was able to kind of pick up his work and start iterating on some of the last pieces I needed to get things to work. So again, the key takeaway is that this executor teaches Snakemake how to run jobs in some other kind of scheduled batch system. All right, so here's what it looks like. Snakemake is run at the access point. You run Snakemake, you provide it the snake file, maybe a configuration file, these other things. It takes its notion of a job and it converts that into a submit file. An important thing to know here is that Snakemake is going to set itself as the executable. So Snakemake gets run both at the access point and it'll eventually get run at the execution point. The way Snakemake does this is by creating a set of job arguments that it passes to itself at the execution point that scale back the total workflow that we might have, all these different rules that need to be run, and it scales it back to run just one unit of work. What are the flags and the arguments I need to do just this one step in the overall process? So it creates the submit file, it places the job, some magic happens, an execution point shows up, and Snakemake at the EP is reinvoked with this specific set of flags that then runs just this one unit of work. In the meantime, Snakemake back at the access point is sitting there and it's watching this job. It knows what its job ID is. It's able to monitor it, keep track of it. It detects if the job has any issues, if it goes on hold, and it gives you some kind of warning then at the access point. Importantly, Snakemake is watching for that output to show up. So Condor is working at the execution point. It's running some kind of a script, some function applied to the input data, and it's going to produce an output. And once this output is produced, that's when Snakemake knows it's time for me to start working on the next step in this workflow and submit the next job. So there was one thing on the previous slide that I didn't mention. What was that? It was that shared file system sitting in between, right? In places like the OS pool, there are no shared file systems. And as my mom always used to say, when you make an assumption about shared file systems, you make an ass out of you, me, and the rest of the cluster. So it was clear that Snakemake had been thinking about this in these types of remote execution environments. And when I was reading the docs, I found this little nugget buried deep in the Snakemake docs. It's a flag you can pass to Snakemake. Shared FS usage, none. I got pretty excited. I was like, cool, maybe this will work for me right off the shelf, right? No. So there was a little bit of engineering still. But one specific thing to note about this flag was that set of job arguments that get passed to Snakemake at the execution point, suddenly these absolute file paths turned into relative file paths. And as I started to explore this, I could see, okay, well, Snakemake does really have the concept of remote execution points that don't share a file system. And they do this in a particular way, but it's just that the way they do it doesn't work with Condor. So the Snakemake way of doing remote execution without a shared file system is for Snakemake to start by saying, there is a remote execution point that is ready to do my work. Snakemake uses this to say, I, Snakemake, will transfer the input files I need to this remote execution point and stage them, make them available for that execution. Snakemake then goes through the process of creating a submit file, hands the submit file off to the executor. The executor then submits the job to the scheduling system, and it starts running at the remote execution point. So this doesn't work in Condor because of that very first thing I said. There is an available remote execution point ready to do my job. In Condor, that doesn't show up until after you've placed the job and asked for some of those resources to be made available. So getting this to work with Condor required a few upstream changes. And I just want to shout out again to the Snakemake maintainers. They're really great to work with. They really care about getting these things to work. They want to see their tools used by the types of people in this room. And so they're willing to help figure out how can we make this better. So the upstream change we made was that we introduced this notion to the executor that it knows how to transfer the files rather than Snakemake being the thing responsible for moving the files. So in this new paradigm, Snakemake tells the executor, in this case HTCondor, that you are responsible for managing, moving, and making available the files that you need to do your work. It then puts these files in transfer input, transfer output files as a part of the submit file, and then it places the job and lets Condor do its thing. So after working through some of these issues over the course of a couple months, things kind of started working. They weren't super reliable at first, but I remember it was Friday at 4:30 p.m. when the first time I saw that the whole workflow ran to completion. And wow, what a great feeling to have spent a couple months working on something and to have it start working at 4:30 on a Friday. There were still a few issues that just didn't sit right with me. The first one is that if I start Snakemake on the access point, and I open up another terminal and I run Condor watch queue because I want to see my jobs running and then completing and then Snakemake submitting the next batch of work, Condor watch queue doesn't pick up any of those jobs that weren't already in the queue when I started running Condor watch queue. So I've asked some of the Condor devs about why this is. We're concerned about querying the sched too often. So Condor watch queue doesn't actually talk to the sched, it watches a log file. But if Condor watch queue every now and then we're able to maybe reach out to the sched and say, hey, how's it going? Got any new jobs I should know about? I think that would be a useful feature. The second issue was the bigger one, and that was that Snakemake is running on my terminal in an SSH session, and if I shut my laptop, Snakemake is a good steward and it does the right thing. It takes all of my jobs out of the queue. It doesn't want to leave zombie work laying around that it's not watching and maintaining. So this next step required a little bit of extra engineering, and I was able to talk to Cole, who's our DAG developer, DAGman developer, and he helped me kind of come up with this process to do something similar to do this similarly to the way that DAGman does it. So I developed this Snakemake long script that kind of has two execution modes, a submit mode and an execute mode. And instead of running Snakemake at the access point, I run this Snakemake long script. It, in turn, will submit a local universe job. So that's a job that's managed by Condor, but that runs at the access point, not the execution point. And then the Snakemake long job running at the access point is the thing that invokes Snakemake. So doing this moves the execution of Snakemake out of my terminal. It moves it into a locally managed job that Condor knows about and can keep track of and tell me about. And then this local universe job does its Snakemake thing, which produces submit files, which sends things to execution points. And from that point, everything kind of looks like what we discussed previously. All right, so there are still a few things that I need to sort out. A lot of this has so far felt a lot like that type 2 research software engineering. And the thing that I worry about, of course, is that today's hacks become permanent as tomorrow's features. So we've started opening this up and working with other groups that are interested in using Snakemake, but I'm kind of at that point where I'm hesitant to see it take off super quickly until I've had time to think about how to fix these issues. So the first issue is that the file transfer mechanisms I've been working out are completely binary. Either everything comes from a shared file system or nothing comes from a shared file system. So in places like CHTC, we have partially shared file systems. Maybe some things have to be managed and moved by HTCondor. And so those types of use cases aren't super well supported yet. I've kind of worked through this problem, but it's extra hacky, and I don't want anyone to know about it yet, or at least know how to find it. The second is that Snakemake doesn't provide a good way to remap file names from one place, from the AP to the EP. So if a mount point in a shared file system is different in these two places, even if there is a shared file system, Snakemake can't handle that. So that's one thing I would like the Snakemake developers to think about handling. The other issue is more of an operational issue, not so much a problem with Snakemake, but a problem maybe with the way we do things in Sprass and the way it's done in CHTC. And that is that these jobs running at the EP, they need to pull down a container, which means that suddenly that EP is hitting these Docker pull rate limits. And unfortunately, the way we're doing this, CHTC has set up these Docker caches so that we can cache frequently used images at the EP, but this kind of bypasses it, not intentionally, but on accident. So that's something we still need to think about. Kind of the next vein of work in the SPRAS stuff is that we want to monitor the resource usage of that inner container. So SPRAS is running in a container at the EP. SPRAS launches that nested container, and really the resources that I care about are what's going on in that inner container. So this has been an interesting conversation with Greg recently. I'm just starting to learn about C groups and some of these other things that go into containerization, and we think we have a way to maybe do this, so that's exciting. And then finally, the big thing is that, okay, I'm going to put on my Pelican hat now. I am a Pelican developer, and none of this works with Pelican. It would be really great if we could figure out how to get this to work. I think the solution to getting this to work with Pelican first involves solving this problem, right? So if Snakemake at the AP is handed an OSDF URL or a Pelican URL, well, we know what the file, the object name at the EP is going to be based on that. So if there were a simple way to kind of strip a prefix out of that URL and tell Snakemake at the EP, this is the actual input that you need to compute on, I think we could get that from there. So one key takeaway I have is that in a lot of the process of developing this and talking with other developers, and I'm guilty of this myself, kind of one common refrain I heard was that, well, Condor already knows how to solve the problem you're asking about. So just rework your workflow and make it Condor-like. I think that's a dangerous sentiment because it's a barrier to entry for our researchers if you tell them, hey, we know you've got this well-established pipeline and it works outside of Condor. Throw that away if you want to come and run in our pool. So one of the difficulties I had was justifying why do we do it this way and why am I not willing to rewrite all of my software to fit it to that Condor-shaped hole. So Greg is known for saying just because you have a distributed hammer kind of makes everything look like a thumb, but I think we should work to make everything not look like those thumbs that we can whack. If you go online, you can check out some of the links that reference the work that I'm talking about, but that's what I have for you today. So thank you.
Any questions for Justin?
Yeah, so Andrew and facilitator of CHTC, I could probably ask you this later, but you know, this sort of, we see people trying to take these type 2 research softwares and workflows and try to run them at scale. And from my own experience in developing that kind of software, because I did my PhD in computational chemistry, I have some of my own software like this. It's usually written to work on my laptop or my desktop. And to try and run it at a larger scale, really without having major redesigns of the software, all you can do is throw more CPUs at it, throw more RAM at it, that sort of thing. And this gets into this tension of, you know, trying to get that software to work on something like HTCondor. And that's where a high performance system is almost a little bit better because you can have one job that's got hundreds of cores and a terabyte of RAM a bit more easily at scale. So I guess this is maybe more of an expression of the tension I feel as a facilitator here. You know, what is the point where we have to ask them to change things about their software? And I know that's a big stretch for some of these folks, especially when they're inheriting it from other people and things like that. But that's a question I struggle with, and I'm curious to know what you think on that.
Yeah, so I think one thing I'll point out, and you touched on this in your last sentence there, was that in the case of SPRAS, these type 2 algorithms that we're interested in running in a kind of unified way are things we don't maintain. They're GitHub repositories that other people have set up. They haven't touched for a decade. They're not really things that we can go in and change. And while we could create a fork and maybe fix some of the things to make it easier, make it more palatable for these distributed systems to run, we don't want to be in the business of maintaining other people's code in that way, right? So I think one of the, as someone maybe more interested in the clean stuff than the stinky stuff, in the computer science than the biology, What I get really excited about with Sprass was this approach that they took to developing a system that makes it easy to run these type 2 research projects. And I think the key there really is the A.out, the containerization, the ability to map from an outside domain into an inside domain. And I think that's a powerful way to think about how to solve these types of problems. If you can get it to run in a container, you can run it at scale. So.
Okay, I think we're really wrong time. So maybe Igor, you can talk to Justin at lunch. So let's have a round of applause for Justin.